very happy to hand over to Laurent, who will show us where we can take it next by combining Klingler and tractography methods. Laurent.
Thank you, Stephanie. Okay, so yeah, so good afternoon, everyone. So what I'm going to talk about now is a mix of exactly what we can study with the Klingler dissection, and also how we can use the same approach as has been developed in the Klingler dissection technique postmortem to apply for some extraction of bundles with tractography. So just to summarize a couple of things that have already been said today, that to get access to the human wild matter anatomy, of course, now you better know that we have access to this with the dissection techniques and with tractography in humans, expecting that we can get something which is so beautiful that what we can do with neuron tracing, for example, in this mouse brain on the top of the slide. Speaking about history, one important thing is that we have to wait for the consideration that the brain was composed of gray matter and white matter before to really consider that a good representation of the brain. So up to that, up to the 16th or 17th century, the representation of the brain was really strange, considering that the cortex has no specific role and that the representation of this cortex was just very naive. Then when the two compartments with the gray matter and white matter were considered, especially with Vesalius at the end of the mid of the 16th century, but then with Vieussens also with at the end of the 17th century, what was important is the definition, or I mean the explanation that what we can get at the bottom of the slide with this very interesting text mentioning that the entire portion of the brain is obviously divided into very small round fibers, and they resemble an ivory comb or church organs. And something very interesting also that is that this was observed in brains of oxen, of other animals, both on raw, on boiled brains, meaning that after, when the dissection techniques was better developed, one important thing was the way you get access to this white matter. Of course, we get in the 19th century, we get a very beautiful representation of these different bundles that have been defined by Reil or Burdak or others. But at that moment, the dissection techniques was still very hard to consider that we can get access to a good representation of the bundles, of the different bundles. Then, as Stephanie presented earlier today, one interesting thing was developed by Klingler, Joseph Klingler. So you already get access to this kind of description that after a good fixation of the brain, and then you're freezing it for a couple of days, then when you are dissecting it at the room temperature, you get better access to the different parts of the white matter, because the ice that you created during the frozen step helps you to define and to follow the different bundles and the different fibers. And when we are saying fibers here, we are not saying axons, but groups of axons represented as fibers. I recommend that you can get access to this paper, which is a very interesting review of the of the work developed by Klingler, and with all the history of the setting up of the dissection method, and of course the book of Ludwig and Klingler, which is a very good reference speaking about dissection methods and good representation of the different bundles. One interesting thing also with that, and I'm going to give more examples that Stephanie already showed you, is that with the emergence of the diffusion MRI and tractography, let's say 20 years ago now, There are new interests of the neuroanatomy and the white matter neuroanatomy, and then some people try to improve the Klingler dissection techniques, especially as Stephanie mentioned, it could be hard to still follow everything when you are following specific bundles and when you are removing step by step the different gray matter, then part of the white matter to study a specific bundle. That could be complicated to follow exactly the termination, the cortical termination of the bundle that you're trying to dissect. And so the team from Hugues Dufaux in Montpellier with Juan Martino, for example, published a very interesting development of this Klingler dissection method, which is called the cortex sparing Klingler dissection method. And in that case, after the regular classical approach that you can remove carefully the gray matter on the brain, then what you're going to do is you're going to keep as far as possible the cortical pieces that you want to follow with the dissections. And in that case, especially for the dissection of the arcuate fasciculus here, so you're going to try to keep the different cortical termination that you are expecting to belong to the arcuate fasciculus. And with this, oh, maybe I forget something. I'm sorry, you should have said that. Should be better, no? So in that case, that you are a very better definition of the different cortical termination that you can get following these Klingler dissection methods. Here is another presentation of the different steps that you can follow and the different layers that you can discover when you are still keeping these different cortical termination. And once you start from the temporal cortex here, then you can follow the different projections and up to the frontal cortex here. You can see the different layers of the anterior segment and the different things that you already dissect virtually a couple of minutes ago now. One interesting also, and this is what I would like to focus today, is that you can also, with this approach, trying to, you can try to specifically follow one specific bundle by locating what we call the stem of the bundle, which is the densest part of the bundle where all the different fibers are converging. In that case, I will take the example with the inferior frontal occipital fasciculus, the IFOF. So the IFOF has been described for the first time at Curran, and showing that the insula, you have a specific configuration where the IFOF was located and projecting for the occipital cortex. And so when you are following a Klingler dissection part, what you're going to do is first to get access to the stem and the dissection locate and to separate the uncinate fasciculus. Going to carefully get access to this IFOF. You can follow the frontal projections and try to figure out exactly what are the a priori. And this is the stem approach that to apply on the tractography data. When you've got your data as a whole brain tractogram, when you are looking at this whole brain, the way that you can you have to draw some could be with a specific definition as you practice with the arcuate. The same approach like the dissectionist for this will be to consider this whole brain tractogram. And we'll first remove a series of streamlines as you will different gray matter at the beginning of the Klingler dissection, where you can remove, for example, from your whole brain frame and the cerebellar fibers, if you are looking for the IFOF association bundle, not something for the so everything crossing the corpus callosum to simplify the tractogram you're going to work on. And you can try to reproduce the same the same way that the dissectionist is locating the stem on the dissection steps by using series of regions of interest to show and to find this equivalent stem on your data. So you're going to use something like this yellow area here, which is the insula, to remove all the fibers which are passing in front of your sagittal view here. And then you can use a series of temporal regions like this, the blue one here, to really clearly see where is this hypoph stem. And then as you draw a sphere on the, to extract some arcuate fasciculus parts in your practice, then you can draw an ROI encompassing all this hypoph stem. And at that moment, then you can be at the same step that when the dissectionist is passing a paper tag to specifically extract the stem of the hypoph during the dissection. And what is important is that if you lose some white matter fibers or some cortical aspects of the brain during the dissection, what is important here is that you can keep your ROI, and then you can go back to the whole brain tractogram from the beginning, because it's virtual dissection. And then you can keep all the fibers which are passing through this stem without any a priori also for this extraction of the hypoph. And so doing so, you can get access to the complete representation of the hypoph by just taking into account all the fibers which are passing through your regions of interest, which corresponds to the stem of the bundle. You can do it exactly for the same way for the uncinate fasciculus, for example, and then you get access to a better representation of the uncinate fasciculus. So this is one, sorry, this is one way to combine tractography and dissection. And especially for this example of the hypoph, it could be shown here that we have a very good representation, a virtual representation of the hypoph, which is very common to what we can extract from a postmortem brain using this Klingler dissection approach, and very similar to the original description from Curran. But it's a qualitative comparison. It's not from the same brain. Of course, you can get access to a postmortem diffusion MRI and try to get some tractography of postmortem, but it's not really an easy way to do it. And so if you need validation of the bundle that you're trying to extract, you definitely need to be more confident by trying to do it exactly on the same brain. And an easier way to do it is to develop a method in animals, in a monkey. And so what I'm going to show you now is that there is a specific question about the existence of this hypoph, of the same bundle that I've just described in the macaque monkey, or in the vervet monkey, which is equivalent. Especially because in these famous books of Schmamann and Pandya, there is no hypoph description. There is no specific description on, and this you've got some part of people considering that the hypoph does not exist in the macaque monkey or in the vervet monkey. So one way to try to demonstrate that maybe we miss this hypoph in the tracing approach that have been already used and described in this type of book. One way is that we can try to do it in the same brain in the monkey. And so we ran this kind of study a couple of years ago now, 2 years ago now, and trying to combine diffusion tractography, diffusion MRI tractography with the micro dissection on the same specimen. And so when we did it on the vervet brain, and one way was first to try to dissect this hypoph using exactly the same Klingler cortex sparing Klingler approach that we already done in the human brain. And by doing this, starting from the posterior part with the vertical occipital fasciculus, which is well known again, also in the monkey brain, then we figure out how to follow the complete connectivity between the ventral frontal cortex and the occipital cortex. And considering that we've got access to the hypoph And so by using exactly the same approach, which means by locating the stem belonging to this specific bundle. And one very interesting thing is that taking this postmortem diffusion data we get on the same brain, we can do the you can run the and compute, sorry, a whole brain tractogram from this postmortem diffusion data, and then we can try to extract the equivalent of this dissected IFOF by using again this stem-based approach. And so if you are locating in a whole brain tractogram of this monkey, this stem here, and just keep all the different fibers which are passing through, we get access to a very remarkable description of this IFOF, which is exactly the same way. And also, as you can see here, you've got a torsion of the fibers from the posterior part before to go and cross the stem here. You have a torsion, and this torsion is exactly the one we get post-mortem for the same specimen by dissection. So we run that in two different monkeys in 4 different hemispheres and observed exactly the same type of tractography IFOF than for the dissected ones. And so this is another approach that you can do to validate the tractography data through a combination of the postmortem dissection and this dissection and the virtual dissection that you can get with the tractography. And of course, for this specific question about the existence of the IFOF, we are now sure that, and a couple of other studies have been published then mentioning that we can consider that there is an IFOF in a monkey brain, as we know in the human brain for more than a century now. And so this is the conclusion of that with with a drawing that we can propose that we have now access to this, and we can have a description of this IFOF, which is complementary to the different old bundles that have been published and described by Schmaman and Pandya in their book. And thank you for your attention. I'd be happy to answer some questions.
Lovely, thank you. Are there any questions? Just raise your hand or unmute. No? So Laurent, I have a question for you. It's true that we definitely need validation methods, but as I've shown earlier, Klingler and tractography suffer largely from the same limitations. Could you think of any other methods that might be a useful tool to validate, or how to better compensate the limitations in Klingler and tractography?
Yes, yes, I do. But it won't be in the human brain for now. There is something that I cannot show because it's very preliminary, but speaking about this IFOF existence in the monkey brain, it is true that we can still consider that it could be a false positive data for both dissection and tractography. So the last step that we just finished the first experiment with is that we injected on the two within the frontal cortex and within the occipital cortex, we injected on some other monkey, of course, 2 different virus, and then with a double tracing, we can show only the axons with where the two virus belong to the same axon. And so with a double tracing like that, we can demonstrate that we have a monosynaptic connectivity between the frontal cortex and the occipital cortex. So I cannot show you, but I can tell you that it works for the IFOF. We have a very beautiful data with monosynaptic connectivity between the cortical termination of the IFOF as we get for the tractography. So we get the data from the monkey first, the in vivo diffusion data. Then we get the frontal and occipital termination of the IFOF on this brain. And then this is where we inject it. And we get the monosynaptic connectivity between, which is the ultimate demonstration, I guess.
It is, it is.
So
I'm going to take your word for it until you can show us the data, but it sounds very exciting.
Yeah, it's coming. It will be soon. But one important thing also is that even in a human brain, when we are describing with Klinger dissection or with tractography, the bundles, we never know if it's a direct monosynaptic connectivity. So that could be it is a very interesting result also in that case. It sounds, and it's intuitive, but for now we have to demonstrate it, that when we are speaking about long range connectivity study with stratigraphy or with dissection, we are speaking about bundles, and we are speaking about fibers which are monosynaptically connected, connecting two regions.
Yeah, lovely. Right. There's no other questions as far as I can see for now.
Yeah, I did.
Hope not. But we're actually perfectly on time for the wrap up. So thank you very much, Laurent. That was super exciting. And I look forward to your new results when they're coming out.
Sure.